Come on, my dears, from today we begin chapter number 2. Title is Alternating Current. Chapter is bit lengthy, very important also, but don't bother at all. I'll explain you each and every article so much in detail and you will be getting lot of confidence in the chapter. If you just work it out through proper practice, then this chapter you may find very easy also. Okay, fine. Let us begin. In textbook, they have started with one article in chapter number 2. From that, if you start, you will never understand the whole chapter. Some of the fundamental facts you need to understand first, and then only you can begin the real content of the chapter. So I would follow that policy. I would like to make certain points very clear first, and then I would proceed further in the chapter. Okay. First, very fundamental fact regarding phasor, I would like to explain you. Look, tell me, what was the equation for alternating voltage in case of AC generator, which you studied in chapter number 1? Remembered? V equals to Vm sin omega t, correct? And here I have written V equals to Vm cos omega t. My dears, please remember, what is this capital V? It is alternating voltage. It should change periodically, correct? But along with sine function, you know cosine function is also periodic function. So you may use V equals to Vm sin omega t, or you may use V equals to Vm cos omega t, no problem. We just go according to textbook. Okay, in textbook they have started with this equation V equals to Vm cos of omega t. Okay, correct. Now in this case, what would be the formula for alternating current? I am showing you. You know current is voltage upon resistance, according to Ohm's law. What is this V? V equals to Vm cos of omega t upon R as it is. Can you rewrite Vm upon R into cos of omega t? Yes. If it is voltage upon resistance, it will give you current. But if it is maximum voltage upon resistance, then it will give you maximum current. I repeat, if you have maximum voltage upon resistance, it should be replaced by maximum current. So in place of Vm upon R, I am just putting Im. This cos omega t as it is, I also as it is. So what is the formula for alternating current? In this case, it is I equals to Im cos of omega t. If V equals to Vm cos omega t, then to pachi I also equal to Im cos omega t. Come on. If V equals to Vm cos omega t, then to pachi I also equal to Im cos omega t. Remember? Fine. Now tell me, what do you mean by current phasor and what do you mean by voltage phasor? First of all, try to understand this word phasor, P-H-A-S-O-R. Phasor means rotating vector. Why we use that vector? Why it is called rotating vector? I'll explain everything. Look. First of all, we want to represent oscillations of this periodically changing quantity like a current or voltage by some vector. How you can say that this quantity is changing periodically? Because in the formula of this current and voltage, you can find out, come on, there is some periodic function. And you know periodic function value changes from, look, 0 to maximum, it decreases from maximum to 0, again it increases on opposite side from 0 to maximum, again it decreases from maximum to 0. 0 to maximum to 0 to maximum to 0. This is how the values of cosine and sine function go on changing periodically. If this value goes on changing periodically, naturally I also will change periodically. Fine. In short, if values of I are changing periodically, correct, you can say as if current is oscillating. Current is oscillating. Because it goes on changing its instantaneous value, we say that physical quantity is oscillating. Now for such oscillating quantity, we would like to represent its oscillations through some vector. That very vector is known as phasor or rotating vector. Now you may say, what is that sort of vector? I am showing you. Look. Consider one vector, say vector OP, correct? It is drawn in such a manner such that its length should be equal to Im. Im means it should be equal to maximum value of current. That is, it should be equal to amplitude of oscillation, because you know amplitude will give you maximum displacement, correct? Fine. Then it should make angle with a positive x-axis just equal to phase of oscillating quantity. What is oscillating quantity right now? Current. And this is the phase. Remember from second semester in the chapter on oscillations, what was the equation for displacement of simple harmonic oscillator? Y equals to A sin omega t plus 5, where 5 was epoch or initial phase. If you take it 0, then y equals to A sin omega t. So what was that omega t? Bracketed term along with sine function. It was nothing but phase of simple harmonic oscillator. Similarly, this bracketed term with this periodic function is giving you phase of this quantity, which is current. And that phase is how much? Omega t. Okay. It is some sort of angle made with x-axis. And now just draw one perpendicular from this head point, and when you draw that perpendicular, the foot of perpendicular I am taking as M, then find out this much component OM. It is nothing but component of Im adjacent to omega t. Component of Im adjacent to omega t, it is Im cos of omega t. Im cos of omega t. Im cos of omega t. It is nothing but I. It is nothing but I. So this is such a vector whose length is equal to amplitude of oscillating quantity, whose angle with positive x-axis is just equal to its phase, and whose projection or component along x-axis or y-axis gives its instantaneous value is called phasor, is called rotating vector. Then now you may ask, why it is called rotating vector? Simple. See, this omega is constant, but as this time passes on, as t will increase, this whole product will increase. And so, if this is the x-axis, this is the phasor, the angle is omega t, and that angle keeps on increasing. So now this vector in the space will be found rotating with constant angular speed omega, correct? Because it is found to be rotating in space, we call it rotating vector. In short, we call it phasor, P-H-A-S-O-R. Fine. A vector whose length is equal to amplitude of oscillating quantity, whose angle with positive x-axis is equal to its phase, and whose component along x-axis or y-axis gives its instantaneous value is called rotating vector or phasor of a given oscillating quantity. Fine. So here this vector OP gives you current phasor, The way you have represented oscillations of current by this current phasor, similarly you can represent oscillations of voltage by voltage phasor. Okay, fine. Now tell me. We begin with that article which is a must for understanding for everybody. Without understanding this, nobody can understand this chapter. Nobody. Okay? You must make it very much clear. What is called a complex number? I am giving you its introduction. Suppose number j is such that its square is -1. Suppose number j is such that its square is -1. Then when the squared number is negative, we must say that number j cannot be a real number, that is sure, because had it been real number, its square would have been either 0 or positive, it cannot be negative. Here it is negative, meaning thereby j is not a real number. A number which is not a real number is known as an imaginary number. Take square root on both the sides. So here it is j, square root of -1. Here j is called, come on, imaginary number. What is j? An imaginary number. Now in mathematics, we have made linear combination of real number and imaginary number, and after that whichever new type of number has been prepared, it is known as complex number. Again, a mixture or linear combination of real and imaginary number gives a number which is called complex number. Okay, so complex number is nothing but it is a function, it is a numerical number which is obtained by linear combination of real number and imaginary number. I am showing you how. Normally complex number is shown by symbol z, and there are 3 ways you can represent a complex number. All the 3 ways today we will see, but this is the first way to represent a complex number. Z equals to x plus jy. Z equals to x plus jy. Fine. Where x and y, they are real numbers. X and y belong to R. Fine. Now tell me, z equals to x plus jy, in that this x, this is the part without j, it is called real part of a complex number. Don't say real number, say real part of a complex number. And this y, which is coefficient of plus j, is called imaginary part of a complex number. Which part? Imaginary part of a complex number. Don't say imaginary number. Y is not imaginary number, y is a real number, but y is known as imaginary part of complex number. Then you may surprise, x and y, both of them belong to real number, both of them are real number. Then why x is called real part and why y is called imaginary part of a complex number? The reason is that you don't have to see x and y, you have to see their coefficients. Come on, what is coefficient of x? 1, and 1 is real. That's why x is called real part of a complex number. What is coefficient of y? It is plus j. And what is j? What is j? J is imaginary number. That's why y is called imaginary part of a complex number. Don't see numbers, see their coefficients. Coefficient of x is 1, which is real. That's why x is real part. Coefficient of y is j. J is imaginary number. That's why y is called imaginary part of a complex number. Got it? Fine. Now for every complex number, we have defined some definite another complex number, which is called it's a complex conjugate. It's a complex conjugate, and then it is shown by symbol z star, and it is defined this way: x minus jy, x minus jy. For every given complex number z equals to x plus jy, a complex number which is x minus jy is said to be its complex conjugate. Is said to be its complex conjugate. Fine. Z star equals to x minus jy. Fine. Now let us see what is the second method of showing complex number. I am showing you. In that second method, which is method of diagram, it is called phase diagram. What is it called? Phase diagram. In that phase diagram, what we do, we just select one plane. We call it complex plane. Normally we select xy plane as a complex plane. In that, given complex number is shown by a point which is called complex point. Suppose it is point P. Fine. Now distance of that complex point from origin, that distance is giving you magnitude of the complex number. Magnitude of complex number is shown by symbol mod z. Fine. Let it be equal to r. We just denote it by another symbol, say r. Now just draw one perpendicular here on x-axis. You know horizontally it is always x coordinate, vertically it is always y coordinate. Horizontal distance x coordinate, vertical distance y coordinate. So this much is x and this much is y. But what is x here? Real part of complex number. What is y? Imaginary part of complex number. Now here in this complex plane, x-axis, positive x-axis is always taken as real axis on which real part is shown. And this whole y-axis, including positive y, including negative y, whole y-axis is known as imaginary axis, and there on y-axis we just show imaginary part. An axis on which real part is shown is called real axis. An axis on which imaginary part is shown is called imaginary axis. Fine. Now take this angle as theta. Okay, fine. And now tell me, what is the component of r adjacent to theta? Will it not be r cos theta? Yes. And that component is this much, which is nothing but x. X equals to r cos theta. Component of r opposite to theta, it is r sin theta, and it is this much, which is also y. I repeat, x equals to r cos theta and y equals to r sin theta. X equals to r cos theta, y equals to r sin theta. Okay. Suppose we want modulus of z, okay, mod of z, suppose. Then in this right angle triangle, this is nothing but hypotenuse, and square of hypotenuse according to Pythagoras theorem will be equal to summation of squares of remaining two perpendicular sides. So mod z square will be equal to x square plus y square, x square plus y square. Come on, mod z square will be equal to x square plus y square. I repeat, in this right angle triangle, square of hypotenuse will be equal to summation of squares of remaining two perpendicular sides. Mod z square will be equal to x square plus y square. Fine. Now, mod z equals to, if you want mod z only, then you should take square root. Take square root on both the sides. So when you take square root here, it is mod z. And when you take square root here, under root of x square plus y square. Fine. Now tell me from here, how would you speak out this result in words? Magnitude of any complex number is always equal to square root of summation of squares of its real and imaginary parts. I repeat. Magnitude of any complex number is always equal to square root of summation of squares of its real and imaginary parts. Fine. Now in this right angle triangle, find out just tan theta. It is opposite to theta divided by adjacent to theta. So it is y upon x, y upon x. Fine. Just speak out in words. What is y? Imaginary part. What is x? Real part. My dears, though this is a very small equation, will be very useful to you in the later part of this chapter. So please remember anyhow, tan theta equals to, come on, imaginary part upon real part. Now suppose I want this product. Which product? I want z into z star. Okay, no problem. Let us find out. What is z? X plus jy. Z is x plus jy. What is z star? Z star is x minus jy. Come on, z star is x minus jy. Come on, don't you know? A plus b into a minus b. What is it? A square minus b square. Similarly, x plus jy into x minus jy. It will be x square minus j square y square. X square minus j square y square. Okay, x square minus j square y square. But j square is how much? Minus 1. Put it here. J square is minus 1 minus minus plus, so it is x square plus y square. But what is x square plus y square? It is nothing but mod z square. X square plus y square can be replaced by mod z square. Put it here. This part is replaced by mod z square. Now take square root on both the sides. Square root of this is mod z, and square root of this I have written here under root of z into z star. Speak out in words. Magnitude of any complex number can always be written as square root of multiplication of that number and its a complex conjugate. I repeat. Magnitude of any complex number can always be written as square root of multiplication of that number and its a complex conjugate. Fine. Mod z equals to under root of z into z star. Now, in the third way of representing complex number, we are supposed to use one result. That result is not derived in the textbook. Nobody will ask in the examination. Just for your kind knowledge and understanding, I am just giving that proof over here. Look, what is that result? Extra problem we are doing here. Extra question. Prove that e raised to j theta equals to cos theta plus j sin theta. How to prove? I am showing you. What is small e? Base of natural logarithm. What was the value? 2.718. What is j? J equals to under root of minus 1, which is imaginary number, and theta is some sort of angle. Okay. Let us start this way. Suppose this right hand side, I just take it equal to y. So this function, I just show it by symbol y. Fine. Now just take d by d theta on both the sides. When you take it here, it is dy by d theta. Come on, when you take d by d theta of cos theta, it is minus sin theta. Derivative of cos is minus sin. J is constant. D by d theta of sin theta, it is cos theta. Derivative of sin is cos. Now in place of this minus 1, can you write? In place of this minus 1, can you write j square? Yes. So in place of this minus 1, I am putting j square. Sin theta as it is plus j cos theta as it is. Now out of these two terms, I just take j common. Inside the bracket left from here it is cos theta plus left from here it is j sin theta. J sin theta. Now this j as it is. But what is this? Cos theta plus j sin theta. Cos theta plus j sin theta, it is nothing but y. So this can be replaced by y. And now take this y in the denominator. Take this y in the denominator. Take this d theta up. So it is dy upon y. Dy upon y. Dy upon y. Look, dy upon y. This y I am bringing down. Come on. Dy upon y will be j into d theta. J into d theta. Fine. Dy upon y is j into d theta. Take now integration on both the sides. Integration on both the sides. Integration 1 upon y dy. Integration 1 upon y dy. J as it is. Integration 1 d theta. Integration 1 d theta. Fine. Integration 1 upon y dy. Its integration is natural log of y. Natural log of y. J as it is. Integration 1 d theta gives you theta. And now just take antilog on both the sides. Antilog on both the sides to the base e. Antilog and log will cancel, giving you y. Antilog of x, then it is e raised to x. Antilog of y, e raised to y. Antilog of j theta will give you e raised to j theta. I repeat. Antilog and log will cancel, giving you y. Antilog of x suppose, then it is e raised to x. Antilog of y, e raised to y. Antilog of j theta, it will be e raised to j theta. Give it equation number 2. From equations 1 and 2, you can see the left hand sides are same. When left hand sides are same, right hand sides will be also same. So e raised to j theta will be equal to cos theta plus j sin theta. That is what we have proved. e raised to j theta equals to cos theta plus j sin theta. From equations 1 and 2, e raised to j theta equals to cos theta plus j sin theta. Okay. And now we are going to use this result. What is the third way of representing a complex number? Z equals to x plus jy from the basic definition. Z equals to x plus jy. Fine. And now put the value of x. What is the value of x? X equals to r cos theta. Put the value of y, r sin theta. Come on, x equals to r cos theta, y equals to r sin theta. Take r common. Inside the bracket cos theta plus j sin theta. Now in place of r, what you can write? In place of r, what you can write? Mod z. So in place of this r, I am putting mod z, and this cos theta plus j sin theta, recently we have proved cos theta plus j sin theta can be replaced by e raised to j theta. So this whole bracketed term is replaced by e raised to j theta. Correct? Z equals to mod z e raised to j theta. Z equals to mod z e raised to j theta. This is the third way of representing a complex number. And now a little example. Find real and imaginary parts of 1 upon z. Let us start with 1 upon z. Okay. 1 upon z already I have written here. Just multiply numerator and denominator by complex conjugate of z, that is multiply by z star. Multiply by z star here also, here also. What is z star? Z star, from the definition, what is z star? X minus jy. Z star is x minus jy. Z into z star, z into z star, z into z star. Z into z star can be written as x square plus y square. Come on, z into z star, it is nothing but x square plus y square. Correct? Now tell me, there is a theorem in mathematics. If z is a complex number, then its reciprocal is also a complex number. Here this z is a complex number, so its reciprocal 1 upon z also must be complex number. Let it be shown by symbol z1. And now just separate the denominators, this upon this minus this upon this. Come on, x upon x square plus y square, x upon x square plus y square. And here I am writing plus j into bracket minus y upon x square plus y square, plus j into bracket minus y upon x square plus y square. Okay, fine. Why I did like that? Why I am finding plus j coefficient? Because coefficient of plus j will give me imaginary part. That's why. Fine. And now the part without j, it is real part. Let it be x1, and in the part with j, the coefficient of plus j is going to give you imaginary part. Let it be y1. So this I am replacing by x1, this I am replacing by y1. z1 equals to x1 plus jy1, where x1 is the real part and it is this much, x upon x square plus y square. y1 is imaginary part, which is this much, minus y upon x square plus y square, minus y upon x square plus y square. Come on my dears, let us proceed further in chapter number 2. Today one very important theory we are going to study. It is completely mathematical. So if you practice it by writing 2 to 3 times, definitely you will remember. Nothing so difficult. Now the article is about series RLC AC circuit. Series RLC AC circuit. First of all, let us see what do you mean by series RLC AC circuit. Look, series RLC AC circuit. Fine. If one resistor, one inductor and one capacitor are connected in series, and then after it is connected across an AC source, then such a circuit is called series RLC AC circuit. If a series connection of one resistor, one inductor and one capacitor is connected with an AC source, then the whole circuit is called series RLC AC circuit. Series RLC AC circuit. Correct? My dears, it is necessary that these three components are right now connected in series, but the order is not important. Order is not important. You may connect first of all inductor, then capacitor, then resistor, or you may connect first of all capacitor, then inductor, then resistor, no problem. So it may be RLC, it may be LCR, or it may be LRC, or it may be CRL, makes no difference. Okay? If you desire, you can connect these components in parallel also, but that parallel circuit is not in our syllabus. In our syllabus, we have to study about series RLC AC circuit. Okay? Fine. Now, AC source delivers alternating voltage, which is given by this equation, V equals to Vm cos of omega t. You know alternating voltage changes periodically. We just use that equation according to textbook. V equals to Vm cos of omega t. Fine. Resistance of resistor, I am taking R. Inductance of an inductor, I am taking L. Capacitance of capacitor, I am taking as capital C. Fine. Now in this circuit, at a particular instant of time, say at time t, suppose value of current is I, it is flowing in this direction, and exactly at the same moment, the time rate of change of current is suppose di by dt. Fine. Now tell me, don't you know according to Ohm's law, if I amount of current passes through R resistance, then potential difference across the two ends of the resistor is given by V equals to IR. Voltage equals to current into resistance. Instead of V, I have shown the symbol VR. R you must write well below V. Okay, fine. Now, what about potential difference across two ends of an inductor? It is nothing but magnitude of self-induced EMF. What was the formula for magnitude of self-induced EMF? It was L into di by dt, L into di by dt, and that potential difference I am showing by symbol VL. L you should write well below V. Okay. Similarly, potential difference across the two ends of capacitor, that is between plates of a capacitor, is V equals to Q by C. You know formula of capacitance, C equals to Q by V, then V will be equal to Q upon C. V equals to Q upon C. Instead of V, I am just putting the symbol VC. C you must write well below V. Okay, fine. Now, according to Kirchhoff's second law, if you make summation of all the three voltages, then you should get total voltage. Total voltage is equal to summation of voltages applied. So if you make summation of all the three voltages, then it should be equal to total voltage V. VR plus VL plus VC should be equal to V. Come on, VR plus VL plus VC should be equal to V. Mind well, these all voltage values are instantaneous. We are talking about instant t, correct? So these all are instantaneous voltages. Fine. What is the value of VR? Value of VR is I into R. Plus, what is VL? L into di upon dt. L into di upon dt. Correct? Plus, what is VC? VC equals to Q by C. VC equals to Q by C. And what is V? V equals to Vm cos of omega t. V equals to Vm cos of omega t. Give it equation number 1. Now tell me, what is I? Current. That is true. But which sort of current? Is it direct current? No. Alternating current. And formula for alternating current is not I equal to Q upon D. No. Not I equal to Q upon D. That formula you can use for direct current. Here, current formula is I equals to dq upon dt. Come on, I equals to dq upon dt, correct? Right now, alternating current is time rate of flow of electric charge. Time rate of flow of electric charge. Fine. Take d by dt on both the sides. So when you take it here, it will become di upon dt. And when you take d by dt here, it will become d2q upon dt square. d2q upon dt square. Fine. Now in place of I, we should write dq upon dt. In place of di upon dt, we should write d2q upon dt square in this equation number 1. Come on. In place of I am writing dq by dt into R plus L as it is. In place of di upon dt, I am writing d2q upon dt square. This I am replacing by d2q upon dt square plus q upon c as it is. This Vm cos omega t as it is. Okay, fine. Now just divide every term by L. Divide every term by L. If you divide by L here, then it is d2q upon dt square. Here it is d2q upon dt square. If you divide by L here, then it is R upon L into dq upon dt. Come on, R upon L into dq upon dt. Divide by L here also. So it will become q upon LC, q upon LC. Divide by L here also. So Vm upon L into cos of omega t. Correct? My dears, such an equation is known as differential equation. What is it called? Differential equation for given series RLC AC circuit. This is differential equation for given series RLC AC circuit. Now this equation is found to be analogous, similar to one equation of forced motion, forced oscillations. In standard 11, in second semester, you had studied about differential equation of forced oscillations. Remember, differential equation of forced oscillations was this equation. Just recall that equation, d2y upon dt square plus b by m into dy by dt plus k by m into y equals to f0 upon m into sine of omega t. You might have forgotten all the interpretations. So let me remind you, what was y? Displacement. What was b? Damping constant or resistive coefficient. What was m? Mass. What was small k? Force constant. F0 is maximum value of external periodic force and omega is angular frequency of external periodic force. Now tell me, these two equations are quite similar to each other. They are analogous and hence we can find certain mechanical quantities quite similar to certain electrical quantities. So let us make a list of all the mechanical quantities and corresponding similar electrical quantities. Here I am writing all these as mechanical quantities and opposite I have written, come on, corresponding electrical quantity which is analogous. Analogous means similar. Fine. Find out from here. What is similar to displacement? It is electric charge. So in place of y, the similar quantity is q. In place of y, similar quantity is q. Displacement is similar to charge. Now take dy by dt. When you take dy by dt, it will give you velocity. When you take dq by dt here, it will give you current. So velocity is similar to current. Velocity is similar to current. What about acceleration? It is dv by dt. Acceleration A equals to dv by dt. Then you should take d by dt here, it will give you di by dt. Mass, look here. Where it appears here m, there it appears. Where it appears here m, there it appears, come on, L. Mass is similar to inductance. Mass is similar to inductance. Actually it is self-inductance, but normally we speak only inductance. Mass is similar to inductance. What about force? Don't you know? Force is mass into acceleration. Mass into acceleration. So this into this. Meaning thereby here this into this. So L into di upon dt. Come on, L into di upon dt. Correct? And what was L into di upon dt? It was nothing but potential difference or self-induced EMF. So this force, you can say it is similar to voltage or EMF. Fine. Come on. B. Here B is damping constant or resistive coefficient, which is similar to R. R means resistance. Damping constant is similar to electrical resistance. Suppose we want to find out a quantity in electricity which is similar to half mv square. Don't you know half mv square is nothing but kinetic energy? Mass is similar to, come on, inductance. Velocity is similar to current. So in place of m, I have written L. In place of V, I have written I. So it is now giving you half Li square. Correct? Remember what was half Li square? It was magnetostatic potential energy stored in an inductor. Now come on, K is similar to what? See, displacement is similar to charge. Displacement is similar to charge. Mass is similar to inductance. Then it implies that K must be similar to 1 upon C. K must be similar to 1 upon C. Here it is. K is similar to 1 upon C. Correct? Force constant is similar to reciprocal of capacitance. Force constant is similar to reciprocal of capacitance. And did you study potential energy of simple harmonic oscillator in 11th standard in second semester? The formula was half Ky square. Half as it is, in place of small k, you can write 1 upon C. In place of small k, I have written here 1 upon C. And in place of displacement, you should write charge. Because here it is y square, I should write q square. Correct? So what is this? Come on. This is potential energy. And this is electrostatic potential energy stored in a capacitor. Stored in a capacitor. And suppose I want to find out quantity similar to momentum in mechanics. In mechanics, what is momentum? Mass into velocity. But mass is similar to inductance. Mass is similar to inductance. And velocity is similar to current. Velocity is similar to current. Correct? Fine. Now tell me. This is the list of, come on, mechanical and corresponding or analogous electrical quantities. Come on. Now alternating current, you can always write this way, dq by dt. Come on, I equals to dq by dt. Fine. Transfer this. Okay. So dq will be I into dt. dq will be I into dt. Now tell me, we want total charge. So let us take integration on both the sides. Integration dq and here integration I dt. Summation of partial amounts of electric charge will give you total charge. So q equals to integration I dt. Q equals to integration I dt. Fine. Now start from equation 1. Okay. Come on. Divide each term by L. In equation number 1, divide each term by L. Come on. Divide this term by L. If you divide by L, you will get di by dt. Here it is, di by dt. Come on, divide by L here, then you will get R upon L into I. Come on, R upon L into I. Come on, in place of Q, come on, in place of Q, what will you dictate? Integration I dt. Q equals to integration I dt. Come on, Q equals to integration I dt. And when I am dividing by L here, it will become L into C now. L into C. And when you divide by L here, it will give you Vm upon L into cos of omega t. Vm upon L into cos of omega t. Correct? Fine. Now, if you want to write this equation in a complex form, then what you should do? Wherever it is real current, you should replace it by complex current. Complex current is shown by symbol small I. Capital I means real current, small I means complex current. So wherever it is capital I, you can just write small I. In place of capital I, write small I. Here also, in place of capital I should write small I. Fine. So left hand side we have written in a complex form. Naturally, right hand side also we must write in a complex form. Vm upon L as it is, correct? But now you should write complex function for which this is the real part. This is the real part of which complex function? That complex function we should write over here. I am showing you. Don't you know from last time discussion, e raised to j theta, I had proved e raised to j theta equals to cos theta plus j sin theta, cos theta plus j sin theta. Instead of theta, you think of omega t. Then it is e raised to j theta. In place of theta, I am putting omega t. So e raised to j omega t will be cos theta plus j sin theta. Instead of theta, you just write omega t. Fine. So e raised to j omega t is cos of omega t plus j into sin of omega t. This is that complex function whose real part is this, or you can say this is the real part of this complex function. Again, this is that complex function whose real part is this. Speak reverse. This is the real part of this complex function. Correct? So if this is real part, then corresponding complex function is e raised to j omega t. That's why in place of this cos of omega t, you know this is the real part of which complex function? E raised to j omega t. Got it? Fine. Give it equation number 2. Now this equation is in terms of complex current small I. Correct? Right hand side indicates that it is a function, it is a periodic function of time. If given equation is periodic in terms of time, then its solution also must be periodic in time. Correct? What do you mean by solution of any equation? Solution of any equation is that value which again when you substitute in the given equation should satisfy that equation. So here solution of this differential equation means that value of I which can satisfy this equation. That solution in your syllabus you have to just remember that solution. Very simple. I equals to I am e raised to j omega t. I repeat, I equals to I am e raised to j omega t, where I am is the maximum value, it is constant, it is, and here e is base of natural logarithm, j equals to under root of -1 which is imaginary number, omega is angular frequency, t is given time. This is that value of I which if you substitute in this equation can satisfy this equation. Fine. Now we require di by dt here and we also require integration I dt. So let us find out those two values from here. Take di by dt from here, take d by dt on both the sides. So here it will be di by dt, Im is constant, derivative of this part d by dt of e raised to j omega t, remember it is e raised to j omega t into multiplier of time. What is the coefficient of time here? It is j omega. That by the j omega you must multiply. I repeat, Im is constant, d by dt of e raised to j omega t is e raised to j omega t into coefficient of time which is j omega. Got it? Just rearrange it properly. J omega Im into e raised to j omega t. Come on, j omega Im into e raised to j omega t. Correct? Give it equation number 4. Fine. And now we want integration I dt. Integration I dt. So let us find out integration I dt. When you take integration here also you must take integration. Im is constant, integration of this part, it is e raised to j omega t divided by coefficient of time which is j omega. So by j omega you must divide. Here we were multiplying in case of derivative, here we are dividing in case of integration, remember. And now substitute the values from equations 3, 4 and 5 into equation number 2. Start from here, What is di by dt? Di by dt is j omega im e raised to j omega t. J omega im e raised to j omega t plus r upon L as it is. What is I? I equals to im e raised to j omega t. I equals to im e raised to j omega t plus integration I dt. Integration I dt, it is im e raised to j omega t upon j omega. Im e raised to j omega t upon j omega. And this L into C in the denominator as it is, L into C. Fine. This Vm upon L as it is, correct? Into e raised to j omega t as it is. Okay? Now tell me, throughout this equation, which term you can cancel? E raised to j omega t, you can cancel throughout the equation. Correct? Cancel. Now, just multiply each term by L. So it is now Im into j omega L. Im into j omega into L, because I am multiplying by L. When you multiply by L here, L will cancel, giving you Im into R. Im into R. When you multiply by L here, L will cancel, then left is Im upon omega C. Im upon omega C. Then one more change I have made. Don't you know j square equals to minus 1? Anna? Transfer this minus sign here. So minus j square will be plus 1. Minus j square will be plus 1. So instead of 1, you can write minus j square. So instead of this plus 1, I can write minus j square. Minus j square upon j. So what is left in the numerator? Minus j. Here it is, minus j. I repeat, in place of plus 1, I am writing minus j square. Minus j square upon j. So it is minus j in the numerator. Im as it is, omega into C as it is. And because I am multiplying each term by L will cancel. And when I am multiplying by L will cancel, giving you Vm. Got it? Now Im, I can take common. Inside the bracket from here, left is R. From here, left is j omega L. And from here, minus j upon omega C. Minus j upon omega C. Correct? And that equals to Vm. Fine. Now find out Im. Find out Im. Transfer this bracket in the denominator. So Vm upon this bracket. Vm upon this bracket. Vm upon this whole bracket I have written in the denominator. R plus j omega L minus j upon omega C. Give it equation number 6. Fine. Now again start with the same equation. I equals to Im e raised to j omega t. I equals to Im e raised to j omega t. Just put the value of Im, which is this much, correct? Same value I am putting here. Come on, start with this. I equals to Im. In place of Im, I have written this whole part. You can verify. Vm upon R plus j omega L minus j upon omega C. Don't forget, this e raised to j omega t is there in multiplication in numerator. So write it in the numerator, e raised to j omega t. Got it? Give it equation number 7. Now this left hand side is current. This denominator is some sort of resistance, because with resistance you can add only resistance. So this denominator is some sort of resistance. If this is current, this is the resistance, this has to be voltage, because according to Ohm's law, current equals to voltage upon resistance. So form of this equation is very much like Ohm's law, I equals to V upon R. Now tell me, what is this R? What is this R? Resistance of resistor. Resistance of resistor. Fine. Resistance of resistor. Now just all of you please be careful for all these terms. Look here now. As effect of resistor on the current is given by resistance R. Similarly, effect of an inductor on the current is given by this term, which is j omega L, which is giving you effective resistance provided by an inductor. So this j omega L is nothing but effective resistance of an inductor. Fine. J omega L gives you effective resistance of an inductor. We just showed by symbol ZL. L you should write below Z. It is given another name. It is also called inductive reactance of an inductor. Inductive reactance of an inductor. Fine. Similarly, this term gives you effect of capacitor on the current, and that very term is known as resistance, effective resistance of capacitor. Effective resistance of capacitor minus j upon omega c. Minus j upon omega c gives you what? Gives you what? Effective resistance of capacitor. Okay. We just give it new symbol ZC. You must write C below Z. It is given another name, capacitive reactance of a capacitor. Capacitive reactance of a capacitor shown by symbol ZC. Okay. Capacitive reactance of capacitor. Okay. Now in textbook they have given formula of magnitudes of ZL and ZC directly. Let us find out those magnitudes. This ZL I have written as it is, but instead of j omega L I am putting 0 plus j into omega L. 0 plus j into omega L. Any problem? This is 0 only. This is j omega L as it is. When I separate it this way, you must have understood, without j this is real part, and coefficient of plus j is nothing but imaginary part. Correct? Now take magnitude of this. Correct? Magnitude of any complex number is always equal to square root of summation of squares of its real and imaginary parts. So here under root of 0 square plus omega L square. Correct? Fine. This is 0 only. Omega L whole square will be omega square L square. Its square will be again omega L. This is giving you, mind well, not inductive reactance, its magnitude. It is given new symbol now. It is XL. It is XL. What is difference between ZL and XL? ZL contains imaginary part, correct? And it contains value J. J equals to under root of -1. Okay. So this is complex. This is complex. And now when you take its magnitude, it becomes real. It becomes real. Okay. XL is magnitude of inductive reactance, mod of ZL. Similarly, let us find out magnitude of ZC. ZC is minus j upon omega c. Can you rewrite ZC as it is? And this part I am just rewriting 0 plus j into -1 upon omega c. Can you do that? Yes, this is 0 and plus minus j upon omega c. Here it is minus j upon omega c. Correct? Now what is this 0? Real part. Without j, real part. Coefficient of plus j, it is imaginary part. Magnitude of any complex number is always equal to square root of summation of squares of its real and imaginary parts. So here under root of 0 square plus -1 upon omega c whole square. This is 0 and square of this will be 1 upon omega square c square. Its square root will be 1 upon omega c. What does this give? This gives you magnitude of capacitive reactance. Magnitude of capacitive reactance, and it is shown by another symbol Xc, where you should write C below X. Okay. Just remind me, what was XL? Inductive reactance? No, its magnitude. Mod of ZL is XL. Similarly, what is Xc? Capacity reactance? No, its magnitude. Mod of ZC is XC. Okay, fine. Now tell me, what is our resistance of resistor? What is J omega L? Effective resistance of an inductor. What is minus J upon omega C? Effective resistance of a capacitor. And what are you doing here? You are making their addition. And if you make addition, then you will get effective resistance offered by whole series RLC AC circuit to the flow of alternating current. Such an effective resistance is known as complex impedance of the given circuit, shown by symbol only capital Z. So this whole addition, this is R as it is. In place of J omega L, I am putting ZL. In place of minus J upon omega C, I am putting ZC. And the whole addition is now replaced by Z, where Z is called complex impedance of whole series RLC AC circuit. Fine. This R as it is. ZL is J omega L. ZC is minus J upon omega C. Now R as it is. J and J I can take common. Inside the bracket omega L minus 1 upon omega C. Fine. This R as it is plus J as it is. Then tell me inside the bracket, in place of omega L, what you can write? XL. In place of omega L, I am writing XL. Minus sign as it is. Instead of 1 upon omega C, I can write XC. Instead of 1 upon omega C, I am writing XC. Okay. Give it equation number 8. Fine. Now tell me, if Z formula is this, R plus J into omega L minus 1 upon omega C, or R plus J into XL minus XC, what about its magnitude? Come on, take magnitude here. So it is now mod of Z. When you take magnitude of a complex number, you know it is square root of summation of squares of its real and imaginary parts. Real part is R, imaginary part is omega L minus 1 upon omega C. So it is under root of R square plus omega L minus 1 upon omega C whole square. And that is equal to under root of R square as it is. But in place of omega L, what you can write? XL. And in place of 1 upon omega C, you can write XC. Omega L is replaced by XL. 1 upon omega C is replaced by XC whole square. So there are two formula for magnitude of complex impedance. Under root of R square plus omega L minus 1 upon omega C whole square, or under root of R square plus XL minus XC whole square. Give it equation number 9. Okay, fine. Now tell me, from equation 7, this I as it is, okay, Vm into e raised to j omega t as it is, but in place of this whole addition, I am just putting complex impedance of the series RLC AC circuit, that is capital Z. So in place of this whole denominator, I am placing capital Z. When this is current, this is some sort of resistance, this has to be voltage, but mind well, it is complex voltage shown by symbol small v. Normally all the complex quantities are to be shown by symbol small letters. Here small I means complex current, small v means complex voltage, but actually according to me, complex impedance should be shown by symbol small z only. But in textbook they have shown by symbol capital Z. That's why I am putting here capital Z. Though it is capital, mind well, it is not a real quantity. It is, come on, complex quantity. Okay, fine. So once again we get something like Ohm's law, current equals to voltage upon resistance. Okay, fine. Now this I as it is, Vm into e raised to j omega t as it is. But instead of Z, what you can write? There were three methods you could write complex number. Last time we had studied. Third method was z equals to mod z into e raised to j theta. Z equals to mod z into e raised to j theta. Z equals to mod z into e raised to j theta. Instead of theta, I am putting delta. What does delta indicate? I am showing you. It is some sort of angle, but what is that angle? I will tell you. Wait. Now Vm upon mod z as it is. Take this part up in the numerator. Then e raised to j omega t into e raised to minus j delta when you take it in the numerator. E raised to j omega t into e raised to minus j delta. So it is now e raised to j common inside the bracket omega t minus delta. E raised to come on j into bracket omega t minus delta. Fine. Now this I as it is, Vm upon mod z as it is. But if it is e raised to j theta, then don't you know its expansion? It is cos theta plus j sin theta. Cos theta plus j sin theta. Cos theta, instead of theta I am putting omega t minus delta t, omega t minus delta plus j sin theta. Instead of theta I am putting omega t minus delta. Fine. And now tell me, this is complex current, but the actual current which is flowing in the circuit, it is real current. It is real current. That real current is capital I. And if you want to find out real current, what you should do? Take real part of complex current. Real part of complex current. Come on, real part of complex current which is small I. And now small I is this much. And from this much, if you want to separate the real part, it is Vm upon mod z. And now real part in this, you know, it is without j, it is this much cos of omega t minus delta. Fine. So this is the real current, Vm upon mod z, and here real part is cos of omega t minus delta. This Vm into cos of omega t minus delta I have already written. And now mod z formula is under root of r square plus omega L minus 1 upon omega C whole square. Under root of r square plus omega L minus 1 upon omega C whole square. This is the required formula of real current. Still I have not told you what is delta, I am telling you. Last time we had studied about complex plane. We had shown complex number by a complex point, and in that plane we had prepared one right angle triangle, and in that right angle triangle, if you have remembered one formula, short formula, tan theta equals to y upon x. Tan theta equals to y upon x. Now tell me, what was y? Imaginary part. What was x? Real part. So tan theta equals to imaginary part upon real part. Tan theta, instead of theta I am putting delta. It is equal to imaginary part upon real part. Imaginary part of complex impedance, it is XL minus XC, and real part is R. We are supposed to take the ratio imaginary part to real part. So XL minus XC upon R. XL minus XC upon R. Wait. What was the equation of alternating voltage? Equation of alternating voltage was V equals to Vm cos of omega t. V equals to Vm cos of omega t. V equals to Vm cos of omega t. And now tell me, maximum voltage upon resistance. Maximum voltage upon resistance will give you maximum current. Let it be shown by symbol Im. So this I as it is, maximum voltage upon resistance is maximum current Im cos of omega t minus delta as it is. Remembered? In the formula of periodically changing quantity, if you find some periodic function, then bracketed part with the periodic function gives you phase. So this voltage phase of voltage at time t is how much? Omega t. Similarly, with this periodic function, the bracketed quantity gives you phase, but this much will give you phase of current. Phase of voltage is how much? Everybody, omega t, and phase of current is how much? Omega t minus delta. Phase of voltage is omega t, phase of current is omega t minus delta. So if you want to find out phase difference between voltage and current, then you should take this phase minus this phase, omega t minus this. Omega t minus omega t cancels, minus minus plus delta. So what is delta? Phase difference between voltage and current. Phase difference between voltage and current. Which voltage? Alternating voltage. Which current? Alternating current. Which circuit? Series RLC AC circuit. So delta gives me phase difference between voltage and current. And if you want to find out that delta, you can find out from here. Come on, delta will be what? Come on, tan inverse. Delta equals to tan inverse of XL minus XC upon R. Delta equals to tan inverse of XL minus XC upon